about linear transformations. So if I have Rm and I have a linear transformation from Rm, call it T, Rn, then this linear transformation could always be written as a matrix, right? We can always represent it as a matrix multiplication. So there's some, I can replace this T with some matrix A. And if I've got a factor from here, from X, then T of X over here is the same as AX. And we saw how to do this. We take the this A, we take the standard basis, and we look at each of those vectors and look at what the transformation does to that. And that gives us actually an immediate representation of the columns of A. So the columns of A are just the transformation of the first standard basis vector and second standard basis vector. And if you need the domain is a m-dimensional vector space. So this was easy, and we did this a few times. Now, if we're thinking about general linear or vector spaces, and we have this transformation. Let's say the transformation now is not from Rm to Rn, but from U to Z, where these are some general vector spaces. Then we can't do the same sort of thing. We can't turn this transformation into a matrix in the same way. For one, we may not even have a concept of a standard basis in this vector space. And even if we did, let's say we took the transformation of the first basis vector. So if we had some basis that we considered the standard basis, and we took the transformation of that thing is inside V, and V is not necessarily an n-dimensional real vector space. It's not Rn. So we don't get columns, and we can't form a matrix that way. James, I did get your email. I'm sorry I didn't respond to it. I'll send out problems.
Okay.
I was going to do it last night. I haven't got to it yet.
Yeah, I realize I like to send out like in the late as well, so.
Oh, also, we might have a quiz. Are we supposed to have a quiz today and it hasn't shown up yet?
Yeah.
Yeah, it's because I didn't put it on there yet. So I'll do the same thing as I normally do. Screw it up, and then fix it later. Okay. So, let's say that the dimension of U is M. The dimension of V is N. And that means that we can, if we pick a basis for this, let's call it, we'll try to do a script B there, and then script C there. So these are, I should just write this out. So there's M elements from U, and N elements from A. So let's say that these are the bases for the two spaces, or some bases that we picked. Then what we can do in that situation is we can take an element from U and we can get its coordinate vector in Rm with respect to this basis, and we can take an element from V and get its coordinate vector with respect to the basis C in Rn. So we can think of this as applying that bracket operation. So this is getting the coordinates with respect to B. This is getting coordinates with respect to C. And now we can talk about the matrix that corresponds to this, this linear transformation by looking at a matrix that corresponds to the linear transformation that goes from here to here. So if we think about doing this linear transformation and then looking at the coordinate vector that we get as the output here, so going this direction, like this, then there's going to be some linear transformation from here to here that gives us the same result, going this way around the diagram or going this way around the diagram. By the way, the book introduces these. These are called commutative diagrams. So if we can sort of chain the functions that we're specifying in the diagram together, and we get the same thing no matter which path we take. So going from here to here, we get a function, and going from here to here this way, we get a function. Going along this path, we get the same function. These are called commutative diagrams, and the book. It's interesting that the book actually introduces this, although they don't call it that. This is a tool that gets used a lot in much more advanced mathematics. So this is something that it's a very useful and powerful way of looking at things. Anyway. So of course, if we have a linear transformation, there's a linear transformation here. If we have a linear transformation from Rm to Rn, then there's a corresponding matrix that we can represent this by matrix multiplication. The book just calls that M. So in this case, if we take an x from U, and then t of x is something in V, this would be x sub b, the coordinate vector with respect to the basis b. And this would be the coordinate vector of t of x with respect to the basis c. So we can't write a matrix going from here to here, but we can do basically something that's it's almost just as good. So we get a matrix that goes from here to here. And the matrix that we had before when the transformation was just from Rm to Rn was nice because we didn't have to think about how to choose that the basis for representing the matrix. We just used the standard basis for Rm and Rn, and there was no choice there. In this case, there is a choice because we have to choose a basis for U so that we can get a coordinate vector, and we have to choose a basis for V as well. So it's almost as good, but not quite. Okay, so how do we form this matrix? Well, we take the basis here, and we get the coordinate vectors for those in Rm. And then we look at the linear transformation of those, and so what we get is, well, let's see, how can we look at this? What I want is, so I'll take the basis here, and going along this way, I get T1 up to T B. And then I'm taking the basis and I'm looking at what columns I get for each of those. matrix that's going to take a coordinate in Rm, the coordinate vector in Rm, and give us a coordinate vector in Rn. It's this matrix right here. Are there any questions about this? So let's looking at this in general. I'm going to actually skip the examples for today. You can look at the examples in the book. I'll give you some exercises if you want to practice this. We actually had two sections assigned for yesterday, and I only did one, or next week. I only did one, so. Okay, now let's look at the situation where these two vector spaces are the same. So we're looking at a linear transformation from a vector space to itself. So we can represent that like this. And again, we're going to assume that V is an n-dimensional vector space. So we have this way of transforming an element of V into an element of Rn in a unique, completely one-to-one way. It's an isomorphism. So we have this, and then we have the matrix representing the transformation, the linear transformation. Is this clear? You look like you have a concern.
I don't understand. I don't know Algebra later.
Sorry?
Do you have an Algebra today?
I don't actually, not today.
I can just come on Monday. I don't understand. I need to know Monday.
Okay, sure. Okay. So this is our vector space. This is in this case, the domain and the range of the transformation T is V in both cases, or I should say the domain and the codomain. So normally we'd written this something like a transformation that goes from V to V. Domain. This is the codomain. Okay, so just like before, this is going from V to Rn, and that is just what we get when we plug something into this bracket here. I'm gonna call it B. I think I called it C over here. Let's just assume it's B. It's a basis. We pick a basis for B that allows us to represent anything in V as a linear combination of that basis. And the coordinates that we get from that are something in Rn. Okay. Now, in this case, we have really just one choice for the basis. We form the matrix in the exact same way, but in this case, we have this kind of interesting notation. So this is going to be a matrix right here, right? And so going in this direction, going along this arrow right here, is taking something in V and applying the transformation to it. So we take something from V like X, and what we get out is T of X, which is still in V. And when we translate these things down into elements of Rn, we can look at how this linear transformation looks going from Rn to Rn, and that's some matrix, some square matrix. So this is N by N matrix. Maybe it would be good if I did an example of this. Anyway, the book gives this one a special name. I think it's just called the B matrix for T. Where B is our basis. So this is the B matrix And what we've kind of done is we've thought of this bracket as being something that works on vectors. So it works on this vector, it works on a vector with the same space, and it gives us something in Rn. But now we're kind of thinking of it as also a thing, it works not just on objects, and not just on things, but on functions as well. So it's taking this whole sort of picture right here, and it's translating it into this picture right here. This is kind of a powerful idea. The name that we use for that in more advanced mathematics is a functor. It translates not just objects, but the relationships between the objects as well. I just thought it was interesting that the book is using this tool. It doesn't say that it's using it. Okay, so we'll do an example for this. Let's look at a mapping, a linear transformation from, was I using, or maybe I was just calling it P, the lower, how they use it. So P2 to P2. This was the space of all quadratic polynomials, right? The vector space of all quadratic polynomials. So we want to know how this acts on an ordinary element of P2. Ax squared plus bx plus c. So what does it do to this thing? And we should be able to represent it in terms of what it does to A, what it does to B, and what it does to C, right? Because we're assuming this is a linear transformation, and this is a linear combination of elements. It's a linear combination of the standard basis. So what this does is it gives us 2ax plus b. So we could verify if we wanted to that this was a linear transformation. We could do that by taking two elements from the vector space and showing that T of u plus b equals T u plus 2u plus T of b, right? And T of cu equals C of u. But we're actually going to do something a little bit different, but basically works the same. It ultimately means the same thing, which is that we're going to look at what this thing does to the basis vectors. So we're going to choose the standard basis for P2. We're going to see what it does to those basis vectors, and then we're going to translate that into R3 and just get a matrix. And immediately we'll know that it's a linear transformation because there's a matrix associated with it. Okay. So what's the standard basis for this? The standard basis is 1x squared. What does t do to each of these things? So t of 1, 0. T of x is 1. T of x squared is 2x, and you probably already recognize what this linear transformation is. This is just the derivative. So I will take each of these things and translate them into Rn with respect to this basis. And so what do I get? I get the B matrix of T is equal to, what is 0 under this basis? It's 0, 0, 0. What is 1? 0, 1, 0. this under this basis is 0, 2, 0. And there is our matrix. Okay, so this is an example of what we're doing. All right, now let's make this even more specific. So this is the most general way of looking at it, and then we assume that the two vector spaces were actually the same. Now let's think of them as being Rn. This is the situation we're quite familiar with, right? So is there any benefit to looking at the transformation from Rn to Rn through the lens of these commutative diagrams? Well, what would be the corresponding thing if my two spaces were Rn and Rn already? I'm going to translate Rn into Rn. I'm going to do that by choosing a basis. And just like in this case, right, we had translated this whole sub-diagram into this whole sub-diagram by applying the same way of looking at it, by looking at it through the lens of this basis. So we took this and we turned it into something based on this basis. So in this diagram, we'll do the same thing. In both of them, we're going to find the coordinates with respect to this particular basis. It's Rn. And so we're going to have a corresponding transformation right there. Okay. Now something I didn't note in all of these situations is that if we get the coordinates for an element with respect to some basis, we can always take those coordinates and we can translate back to the element, right? So we have another arrow that goes back in this direction. We can always do that. Similarly in this situation. So this was a linear transformation, and in fact it was invertible as well. That was our definition of an isomorphism. Another way to think about that is that we could have taken this picture and we could put Rn up here instead and put V down here. And while we can't form a matrix with V, everything else about the diagram is still the same. That's what's special about Rn, is that we can form columns, lists of numbers, and then we can stack them together to make a matrix. Okay, so if I have this translation into the basis, first of all, let's actually think of this transformation as, we'll think of it immediately as multiplication. I'm going to write that as A times. So this is multiplication by matrix. We know that must be the case. And we can even think of the situation where we start with a matrix and we think about it as a linear transformation in the same context as we did over here. If we go in this direction, what we can do is we can take P to be this V1 up to Vn, right? And going in this direction was multiplying by P inverse, right? If we wanted to find what the coordinates of a particular vector were, if we wanted to, anyway, to get the coordinates, we multiply by P inverse because we had this relationship. P times x sub b, this is equal to x, right? And since the columns of P formed a basis, they're linearly independent, which means this matrix is invertible, yada, 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 so that we could divide it over the other side, or multiply both sides by its inverse. So going in this direction is multiplying by p inverse. Going in this direction is multiplying by p. And now I'll give this, oh, is that a special name or not? I don't know. I'll call this transformation that we get out of this diagram, we'll call it D. And so what does this say? It says that if I look at this transformation according to the ordinary, the standard basis, this is just a matrix multiplication. After I translate to the coordinates with respect to this basis, I get another linear transformation right here. It corresponds to this one. And what's the relationship between them? Well, all of these things, I'm going to put a little dot there to indicate I'm doing multiplication. The diagram, the way we had looked at it was going this way and going this way gets us the same thing. But because these are invertible, because we can go backwards, we can just say that going right here is the same thing if this diagram works. We think it does. Going down this way, across here, and then going back up. What does that give us in this case? It gives us that multiplication by A is the same thing as multiplication. I want to be careful. I'm taking an x and I'm multiplying it by p inverse. So that would be p inverse times x. Then I'm multiplying by this matrix right here. Put it on the left. Sorry. Mute this phone. And then, going up this direction, multiplying by p, and I get a equals p inverse. And we've seen this before. So, we have these two matrices that are related to each other, and in fact they're related by a similarity transformation. A is similar to D. Now we used D before because it's the first letter in diagonal, and we were thinking of these as diagonal matrices. And there's good reason for that. The diagonal matrices are really useful because they're diagonal. So they're easy to multiply, they're easy to find the eigenvalues, and all those things. But this gives us a new way of looking at what these matrices actually are doing. And James, you actually pointed this out in a previous class, I believe, that what we're looking at when we do this is we're applying this transformation, but with respect to that basis. Right? So, that's another way to say this. How's the book say it? Suppose A equals P inverse, which is diagonal, is a diagonal matrix. B is the formed from the columns of, say P, does it say P? Yep. And P is the P matrix, for the transformation that takes x to whatever you get when you multiply A by it. this means is that the transformation that we get from, that multiplying by A gives us is really the same transformation that we get multiplying D by the element instead. It's the same transformation, we're just looking at it from a different basis. In this case, we're looking at it from the standard basis. In this case, we're looking at it from the B basis. And there's the statement, suppose A equals PDP inverse, where D is a diagonal invariant matrix. We can go ahead and cross out the diagonal part because the book goes about it at kind of a different angle, but we get to the same point. Nothing in this diagram says anything about B being diagonal. D is just a letter in this case. So that's the upshot of this section. Okay. So that's it for, let's see. Official way to compute is to compute AB and then we'll reduce the element matrix. Yes. They just note in the book again that computing an inverse is really a computationally difficult problem, and it's easier just to form, what are we trying to form? P, the augmented matrix PAP, and then row reduce to this. Numerically, this is better. It's easier and it's you don't have to compute the inverse itself. So there's a section on complex eigenvalues that we're going to skip because I didn't choose the curriculum for this course. Okay. So that's so that's eigenvalues and eigenvectors. It's very important, deep and fascinating part of linear algebra. But we're going to put this on hold for now and add in another element to the things we talk about in this course. So when you were introduced to vectors, it was probably in calculus. Yes.
So that last part that you just wrote up, is that a way to find D without all the complicated things we did the other day? Is that what that's saying? Because we're reducing it to P inverse AP?
It's
Because we know how to find P pretty easily, right? It was just the algebra to find D.
that's the question. If we know what P should be, if we know what the basis is that we want to look at this with respect to, then yes, this is a computationally easier way than trying to figure out what the inverse is separately and then doing a multiplication. Now, if what we're trying to do is find eigenvalues and eigenvectors, then we can't do it like this because we'll have to know what the eigenvectors are ahead of time. And the only way we have to do that so far is to get the eigenvalues from the characteristic polynomial and then doing that.
All right, thank you.
Yeah, no, that's a good question. I don't know if we're going to get to the point in the semester where we show actually how eigenvalues and eigenvectors are computed in practice, because computing the characteristic polynomial, I mean, you see you get these big polynomials, and computing the roots of these things is very difficult, or if the degree is higher than 4, if the degree is 5 or higher, it's essentially impossible. The best you can do is approximate them. You can use some kind of approximation method to get the approximate eigenvalues. In practice, something completely different is done. So they do an approximation. There's no way to get these things exactly. You have to just crunch away at the numbers, getting closer and closer and closer each time. They do that directly, and in fact, if you use a computer algebra program to figure out what the characteristic polynomial is of a matrix, if it's more than a 2 by 2 or 3 by 3 matrix, very likely what it does is it goes off and computes the eigenvalues and then forms a polynomial that has those as roots, and then gives that to you. So it does it in the exact opposite direction that we do. And one of the things that comes up a lot in linear algebra is that, I don't know why I'm pointing at the board, there's nothing on the board. When we're introduced to these things, we get, computing the characteristic polynomial is work, but it's fairly straightforward. And you can see, why it should have the properties that it has. So it's useful from a very theoretical standpoint. But in actually computing these things, you almost always find that the thing that's useful for theoretical purposes is completely useless for practical purposes. It helps you understand what's going on and prove things about it and come to conclusions, but it doesn't actually help you compute the thing. And so almost always, in practice, things work in the opposite direction. You actually compute things. It seems like, the way we think about them is completely backwards from the way we actually use them. It's a strange phenomenon that comes up a lot in linear algebra.
What was this chapter name? Because I don't remember seeing 2 chapters listed for Wednesday.
It was 5.4.
5.3, 5.4 is what was listed on our page. I think that got updated at some point, so.
Well, I haven't changed it, and I'm the only person who's allowed to. So
Okay.
if it got updated, I did it in my sleep or something.
So it's 5.4?
Yeah, this was section 5.4, and I was supposed to cover it yesterday. That's why we had so much extra time. We could do some examples. But anyway, so now, that's eigenvalues and eigenvectors, which, like I said, is very, it's a really deep subject. There's a sort of question about if you took a really big matrix with random entries, right? You just randomly chose entries, let's say from -1 to 1. And then you computed the eigenvalues of this matrix, how would they be kind of distributed? Like, what would be their distribution if you just randomly chose matrices and then computed eigenvalues over and over and over? And this question of eigenvalues of random matrices turns out to be like mysteriously connected with lots of other areas of mathematics and science. So this is just the tip of the iceberg. But like I said, we're going to move on to go to something that's also interesting, and that is how we initially got introduced to vectors, which was in 2 dimensions and 3 dimensions. Right? It was typically in Calc 3 when we're talking about physical things, right? So we're talking about things in the real world, 3-dimensional space or 2-dimensional space, space in which we have intuitions about distance and size and shape and angles. So angles and distances, those are things that we have intuitions about in 2 and 3 dimensions, right? Now, in order to apply the power of mathematics and logic, we took those intuitions, calculus or whatever, and we turned them into symbols, right? We took that kind of geometric feeling about the world and we turned it into symbols that we could manipulate logically. And we could come to all sorts of conclusions that way. Sometimes this is useful for answering problems. Sometimes, like when you're driving a car, you don't do calculus in your head, right? You don't get out a calculator to compute the best way to drive down the road. You have an intuition for these things. But we don't have an intuition for things like distance and angle in, say, 4 dimensions. You can't imagine what an angle in 4 dimensions would look like, or in 10 dimensions, or 100 dimensions, or 1,000,000 dimensions. So we either, depending on how you look at it, take a leap of faith and say the things that were represented by the symbols that we used to reason about distance and angles and perpendicularity, all of these ideas, those symbols captured it perfectly for 2 and 3 dimensions. Whatever it is in the higher number of dimensions, it must be whatever those symbols represent. The symbols don't care about what the number of dimensions are, right? to say that in 2 dimensions, let's draw coordinate axes. It's been a while since we've drawn the coordinate axes. So we got something that's 45 degrees above and 45 degrees below the x-axis, and these things should be perpendicular. Nowhere in all of the linear algebra that we've done have we said anything about angles, right? It's always just been a list of numbers. So what's the number that corresponds to this? I'm going to make these look like the same length. So if we do that and we say this is 1, and this is 1, and this is -1, then this vector can be represented as 1, 1. And this, I should say a line segment really, can be represented as 1, -1. And the way we represented in symbols that these were perpendicular was with the dot product. We take the dot product of these 2 things, and we say if this thing is 0, then they're perpendicular. So this was equal to 0. And the way we did it was we would multiply 1 by 1, and then we would add 1 times -1, and of course that was equal to 0. That was the dot product. Okay. Now we can represent the dot product in a very straightforward way. Let me take a step back. When we say things are perpendicular in 2 and 3 dimensions, because we know what perpendicular means. Before you ever took a math class, you knew what perpendicular was. When we proceed forward, we think about them in a more abstract way, and so we kind of slowly transition to using a different word, and we call it orthogonal instead. They mean the same thing, assuming that they mean the same thing in 4 dimensions and 100 dimensions and so on. So we have another name. This was the dot product. We're going to consider it more abstractly, and therefore we're going to come up with a different name for it for absolutely no reason at all. But we're going to call it the inner product. It's not totally for no reason at all. For example, there was a dot here. If it wasn't a dot, we would have called it something else. The way that we can represent this dot product or inner product in Rn is we think of these things as matrices. So this is well, we didn't even write them like a column vectors in calc, right? So we can think of these as matrices. This will be a 2 by 1 matrix. Okay, so this is 2 by 1, and this is 2 by 1, right? And then what we'll do to do the multiplication is we'll do a transpose of the first thing. And so what we end up with is 1, 1 times 1 minus 1, like this. So a row vector times a column vector. And so now in this case, this is a 1 by 2. This is a 2 by 1. And we can go back to the old days of a month ago and see that this multiplication makes sense. The inner 2 things match up. So when we do the multiplication, they kind of collide and disappear. And what we get is a 1 by 1 matrix, which we're going to just think of as a scalar. And we also call this thing the scalar product as well. And then we get so this is how we're going to do something like a dot product. And if you remember the dot product, A times A dot B, and then we divided it by the size of A times the size of B. This was equal to the cosine of the angle between A and B. Boom. We just blow it up to whatever number of dimensions, because there's nothing that says that these have to be 2 or 3 dimensional, right? As long as they're the same number of dimensions, we do the multiplication. So now the concept of angles that we have from the real world has suddenly been expanded to the concept of angles in any number of dimensions. 4 minutes left. Okay, I'll do this. So we're going to continue this on Monday, and we'll mix it in a little bit with 6.2 as well. There's some properties of this. I'm not going to verify them. You can verify them for yourself. They're easy, kind of easy to see. U dot V equals V dot U. U plus V dot W equals U dot W plus V dot W. Cu dot V equals C times U dot V, where C is a scalar. And this is the same as U dot CV. And finally, and this property is possibly much more important than the other properties. U dot U is positive. Non-negative, I should say non-negative. U dot U is at least 0, when we're thinking about a real number. And U dot U equals 0 if and only if U is itself the 0 vector. So when we dot a vector with itself, it's always something that's positive unless it's the 0 vector, in which case it's 0. In other words, nothing is perpendicular to itself except the thing that doesn't point in any direction at all. All right. Oh, one reason for calling this the inner product is because this is an inner product. So we can define the inner product in lots of different ways, and if we think about other vector spaces besides finite dimensional real number lists of real numbers, then there are other ways that we can define the inner product that are different. In fact, if we look at vector spaces of functions, which is one of the examples that we looked at, then this kind of inner product actually sort of doesn't make sense. But that's just one reason for the terminology. And I mention that because we're next going to talk about the length. So instead of underlining, I'm going to put it in quotation marks. Or norm I'll underline. So this is, we think of this as the length of a vector. We do it with double brackets. I don't remember if we use single bars or double bars in Calc 3.
I think we did
Double? Okay. Well, this will be the same definition of a norm. And that is equal to the square root of V. Let's even write it like that. V transpose V. Actually, we'll switch back. And I'll tell you why in the last few seconds of class. So this was square root of V1 squared plus V2 squared plus Vn squared. Matches exactly with the definition from Calc 2. Now, again, in this situation, I want to I want to say, this is a norm. It's a particularly nice norm. It has a lot of very useful properties, but it is not the only way that we define length in an n-dimensional vector space. It's the one that corresponds in 2 dimensions and in 3 dimensions to the way we think about length. So this is the Pythagorean formula, for example. That's the one that corresponds to the way that we feel about what length should be. But it's not the only one. So I just want to say that without any explanation of what else there could be. Just one last thing. The reason I switched from the dot here instead of the transpose is this right here. So what we get out is something that we can compare to 0. What we need in order to do this is we need a number system where it makes sense to say that things are positive and things are negative. For example, we've talked throughout this class about the possibility of using complex numbers instead. If what we got out here at the end was a complex number, we can't say whether it's greater or less than 0, because as Laura pointed out in the previous class, greater or less than 0 just means to the left or to the right on the number line of 0. Right? I might have got those mixed up, but you know what I mean. So we can put these things on a line and say our number's right here and 0's right here, so it's got to be a negative number because we gave this the negative orientation. But the complex numbers take up the whole plane. And so to the left of this one right here, is it to the left or to the right of 0? Well, it depends on which orientation you're looking at the plane from, right? So it no longer makes sense. In the case of complex numbers, to do the inner product, instead of doing just the transpose, we would do, I don't want to do an example. So in the case of real numbers, it's just the square root of v transpose v, so that's some scalar. In the case of complex numbers, this is v star v. So what we do is we take the transpose and then we flip all the entries to their conjugate. And if you multiply a complex number by its conjugate, you may remember you always get a real number. And in that case, we are guaranteed to get something like this. So we will get a real number out at the end. The real number will always be a positive number or 0. I think I'm going to stop there.